of a bit of a ways to go in terms of the convergence analysis of gradient descent, so let's just jump right on that. So here's the statement that we're going to prove. If f is convex and differentiable, and its domain is everything, and additionally, its gradient is Lipschitz. Remember, this is something that you actually encountered on homework 1. That means that if I evaluate the gradient at x, and I evaluate the gradient at y, and I take the norm between those two vectors, that has to be bounded by L times the norm of x minus y for all x, y. That's what it means for the gradient of the function to be Lipschitz with constant L. Then the following holds. If I were to take any fixed step size that's smaller than or equal to 1 over L, then after k iterations, what I see when I evaluate the function at xk is the kth gradient descent iterate minus f star, which is the, remember we use that to note the optimum of the function, is bounded by the distance between x0, where I started, and x star, this is any solution x star, squared, divided by 2 times t times k. Okay, that's what we're going to prove. There's nothing asymptotic here. This is a bound that holds for all k. One thing that I'm not going to be particular about in this proof, and also in all the convergence analyses that we give, is that we're always going to assume that the solution exists, that a minimizer exists. So remember we said that not all convex functions achieve their optimum, right? So it could be off somewhere at infinity. Kind of hidden behind the scenes here, as we're saying, let's assume that it does. Okay, so that's, I'm not going to ever be explicit about that, but that's just going to be always the case when we're looking at rates. So when we look at this statement, the lingo that we use for describing this convergence rate is that gradient descent converges at the rate 1 over k, order 1 over k. It means that after k steps, I can expect to see a descent between, I can expect to see actually a suboptimality bound for where I end up after k steps of gradient descent compared to the optimum that is on the order of 1 over k. Okay, treating everything else here like a constant. Another way of saying this, which is I think the more common way of thinking about this kind of rate, and the way I prefer to remember it, is that if you ever wanted to get a suboptimality bound of epsilon, this tells you that you need on the order of 1 over epsilon iterations. Right? Just set this equal to epsilon, set this right-hand side equal to epsilon, and solve for what k should be in terms of epsilon. How many steps do you need in order to guarantee that the right-hand side is equal to epsilon? You'll see that k is basically, again, just, well, right here. K is equal to the square distance between where you started in a solution divided by 2 times t times 1 over epsilon. So we need on the order of 1 over epsilon iterations to guarantee epsilon suboptimality for gradient descent. OK, let's prove this now. Actually, the proof is not too bad. And it starts off from a fact that you proved on homework 1, or that you're proving as we speak, I guess. And for homework 2, you're going to reproduce kind of somewhat similar proof. The details are different, but at a high level, they're doing similar things for the subgradient method, which is what we'll learn 2 lectures from now. So I've written down the key steps of the proof in the slides. I'll kind of fill in the details on the paper. This might be the only convergence analysis that we do in detail for first-order methods. I'm pretty sure it will be. I just wanted you to see at least one, kind of in-depth portrayal of how we prove such a theorem. Everything else we're just going to state results and not prove them. And I have some high-level details in the slides that you can follow if you're interested in seeing how you prove the other results. OK, so the very first thing we do is that we claim that because f is Lipschitz, actually rather grad f is Lipschitz with constant L, that implies the following. In fact, you guys showed on your homework that this is actually equivalent these two statements are equivalent, or like I said, you're proving that now, that f of y is less than or equal to f of x plus the gradient of f of x transpose y minus x plus L over 2 times the square distance between y and x for all x and y. So this says that our function is upper bounded by a quadratic, and that's this quadratic. Okay, now we can start to see the connection to the pictures we drew earlier. We were trying to iteratively replace our function by a quadratic. Okay, and let's go ahead and let's plug in y equals the gradient descent update. So if we were at x, we're going to see what happens to our upper bound if we were to take a step in this direction, negative t times the gradient of f of x. So if y is equal to x minus t times grad f of x, then we're just going to see, let's actually call this x plus as well, because that's the notation we're going to use. It's just x plus denotes the next iterate for gradient descent after x. That this upper bound tells us that f of x plus, so I'm plugging in y is equal to this value, is less than or equal to f of x plus, here I have y minus x. So if I take y minus x, then I'm going to see that's equal to, it's going to be negative t times the gradient of f of x. And I have that transpose the gradient of f of x. So I get minus t times the gradient of f of x in norm squared. That just came from this term. And from this term, I'm going to get plus L times t squared over 2 times the gradient of f of x squared. Again, because y minus x is going to be equal to negative t times the gradient of f of x. So I just plug that in here and here to get these expressions. Okay? So we should all be on the same page here. Okay, and all I've done in the slides is I've actually rearranged this. I've just said this is this upper bound is I'm going to write this as follows: 1 minus L t over 2 times t times the norm of f of x squared. Okay, let's pause and let's now convince ourselves that we've done something useful. What happens if t is less than or equal to 1 over L? What have we shown here in this expression? What happens if t is equal to 1 over L? Start with that. What is this here? What does this whole term look like? No, because I have an over 2 here. So I have, so what I'm going to get is this quantity actually. So let me first just write it out here. Then the right-hand side is going to be looking like this, right? If t is equal to 1 over L, I just get 1 minus a half times t. I'll just leave that as t. I don't really care. And I have a negative sign up front, so I just get this. Okay, so this is what happens if t is smaller than or equal to 1 over L. We get this bound. What has this told us? Why is this useful? It's because we've shown that we've actually strictly descended on the function. Right? Where I am at the update, that should be x plus on the inside, is where I was before, minus something positive, if t is positive. So this is actually a useful kind of side conclusion we got from this upper bound. Every step of gradient descent makes the criterion smaller by some strict amount if t is positive. But that's only true if t is less than or equal to 1 over L. So the step size has to be small enough in order for that to be true. Now we can see, again, why we have that condition in the theorem, and also what that means in terms of the upper bound. Right? That means something in terms of the upper bound actually majorizing, that upper bound quadratic majorizing our function. OK, so let's from now on, let's think about t between 0 and 1 over L. And actually, we're just going to use this fact. I don't know why I put it in brackets, but we're going to use this fact. And we're going to use convexity of f to get the following expression. So let's use the convexity of f at the point x to get an expression that relates f star and f of x. So how do we do that? What is the relationship between f star, which is f of x star, and f of x if I use the convexity, first order expression for convexity of f? What do I write here? I'm using convexity of f at the point x, and I'm using like y as x star. Yeah. Almost. So, okay, let's just write out the linear function here. This is f of x plus grad of f of x transpose x minus x star. But what's the right direction here? Right. Right, so it lies above its tangent line. Tangent line is a global underestimate of the function. This is just by convexity. So in other words, let's rearrange this to say f of x is less than or equal to f of x star. And I'm going to actually OK, I already flipped it by accident. So you guys were just being nice and didn't call me out. So the expression is f of y is bigger than or equal to f of x plus grad f of x transpose y minus x. And I'm just applying that here to y as x star to get this inequality from the definition of convexity. And now I'm going to move this to the other side just to get an upper bound for f of x. And in doing so, I'm just going to write the negative of this term by flipping x and x star. Okay? So this is an upper bound on the function f. And I'm actually going to apply that upper bound right here. So I'm going to conclude that f of x star, or f of x plus, rather, sorry, from this expression, which just came right from upper bound from the Lipschitz of the gradient and the right choice of t, is less than or equal to, let's plug in this upper bound for f of x star, plus the gradient of f of x transpose x minus x star minus t over 2 times the gradient of f at x. Okay, so far we've used just really elementary definition of convexity and an upper bound from the Lipschitz gradient. And this is what we've arrived at. So this is starting to look good, right? We're starting to upper bound where we are at, some gradient sun update compared to what the optimum is. And we can call this f star. That's fine. And now I'm going to claim actually that this right here is equal to f star plus 1 over 2t times the difference between the square distance between x and x star and the square difference between x plus and x star. Okay, I'm going to claim actually these two formulations are completely equivalent. So let's just check that. Okay, and we can just check this by plugging in x plus, which is x minus t times grad f. Okay, so, and actually we're just going to expand that term to see that that's true. So what happens if we expand this term? Then we get x minus the norm of x star squared. So I'm going to actually group these two. You can see why I want to do that, because that's going to cancel out with this guy, right? And then I can write this as, say, minus this times the cross term. So it's minus t times the grad of f of x transpose x minus x star. But actually, right, okay. Plus the norm of this term squared, t times it's going to be t squared times the grad of f of x squared. So this just came from expanding this out. Okay? And now we're going to see that if we were to plug this back into our expression, then this first term is going to cancel with this first term. This second term, if I take negative 1 over 2t times the second term, I'm going to, oh, I missed a 2 here, thank you. I'm going to exactly get positive grad f transpose x minus x star, which is this. And the third term, I'm going to get exactly minus t over 2 times the norm of the grad squared. Okay, so I've just checked that actually these two formulations are equivalent. So all that I got this from, we could have also gone from here to here, but I just thought it was easier to go the other way, is that you could have plugged in what x plus is and tried to figure out what this was in terms of x plus. Okay, so now we've arrived at this. I'm going to write this in terms of iteration k, so I think it's easier to see that way for iteration k. At xk, we have the following. F of xk minus f star, I'm just going to read off this bound, but written in terms of iteration k, is less than or equal to 1 over 2t. I guess I can call it, I'm going to leave it as t because we're thinking about taking the step size as being fixed in this proof. Xk minus x star squared minus xk plus 1 minus x star squared. All right, that's what we've just proved. So again, just at a high level, what have we done? All we've used is the fact that we have an upper bound on the function from the fact that its gradient is Lipschitz. That is something you have established on homework 1. And we've used the fact that the step size is small enough that upper bound gives us a really tight inequality, which is this one right here. So that step. From here, we just upper bounded f in terms of f star, because we eventually want to compare how well we're doing to the optimum, right, using the definition of convexity. And then there was just a bit of trickery to realize that our upper bound could be written in terms of actually differences between the squared distance at x and the squared distance at x plus, the next update to x star. And that gave us this expression. It's a very nice expression. What would you do now if you had this in a proof? What would be my next step? So I kind of gave it away in the slides. I often do that. We just would sum this over all k. Right? This was wrong. This is supposed to be xk minus 1, and that was supposed to be xk. Right? Where we are now, where we are before, where we are now. So let's sum this actually over all I, going from 1 through k. Maybe I'll write it as I just so that it's clear. Okay, so at iteration I, for any I, we've proved that this bound holds. So if we sum this, you're going to see we get a telescoping sum here, right? This term is going to cancel out with the term from the next element of the sum. And so we're going to get the sum of f of x, should say I going from 1 through k, is less than or equal to what's going to remain here. All that's going to remain is the very first term. This came from the bound for f of x1. All the intermediate terms are going to cancel, and all that's left is going to be the term involving xk. Okay? Now we're actually very close to proving the result. We're very, very close. We're just going to get rid of this. This is actually, it can only be negative, right? So we're going to say this is actually less than or equal to 1 over 2t times the square distance between where I started and a solution, x star. So that's still a valid bound. It's a little weaker, but it doesn't really matter. It's still going to give us the result. And we're going to use one more thing, which is that since these guys are monotone decreasing, why are they monotone decreasing? We actually just proved that here, right? That was this important fact that I put in brackets. I'm going to officially remove this from brackets because I guess we used it in more than one place. We proved here that at every iteration we decrease the criterion according to gradient descent. So that's what I'm just stating here. They're monotone decreasing. I'm going to claim that this actually is going to be bigger than or equal to, say, k times f of xk minus f star. Right? Because we're only making it smaller after each iteration. So that's going to tell us that f of xk minus f star, say, is less than or equal to, another way of saying that is less than or equal to 1 over k times this quantity, which in turn I'm going to say is less than or equal to 1 over k times this quantity. And so that's going to give us a result. So it's actually very important here that we saw that we had a monotone sequence for the gradient descent updates. Questions? Okay, this kind of thing may have looked strange if you've never seen it. But this is really a very prototypical outline for a proof. You start by upper bounding the function you're trying to minimize, usually with a quadratic, because quadratics are easy to analyze. And you prove that under a kind of appropriate choice of step size, the upper bound gets small, hopefully small enough that actually you show that the algorithm that you're analyzing strictly decreases at every iteration. That's all we did to start off with, right? How did we achieve such an upper bound? We achieved it via this Lipschitz condition on the gradient. And as you see in the homework, it's actually equivalent to this Lipschitz condition. And then it's a matter of choosing the right step size to make the upper bound small, which is what we did. And it's a matter of now taking whatever this upper bound is and relating it somehow to the optimum. We have to relate it to the optimum because we want to know eventually how far we are away from the optimum. And typically that's done with definitions of convexity. Okay, it's the same thing you're going to do in, say, the proximal gradient proof or the subgradient proof. We use definitions of convexity that relate f of x to f of x star. And from then on, it's just a matter of adding up what we got for iteration I over all iterations. So iterating this bound to get a bound on how far you are in an absolute sense at iteration I versus f star, which is what we ended up with. Okay, if there's any questions, you guys can come talk to me or anyone in the TAs. I actually have office hours after class. We can talk about it then too. So we have a bit of time now, which I want to use to go over the other results for gradient descent and maybe a bit of connections to some approaches in machine learning and statistics. So let me just tell you the other results. The proofs of these are not in the slides. The proof of for this one on backtracking is actually rather straightforward now that you learned the proof for fixed step sizes. And the proof for the next result was on a homework from last year, so you can take a look at that actually if you're interested, or the Boyd and Vandenberg textbook, see how that's proved. So let's go through a couple more results. If we make the same assumptions about our function, gradient is Lipschitz with constant L, it's smooth and convex, full domain, then if we use backtracking line search instead of a fixed step size, we get essentially the same rate. That's what this tells us. We don't lose much. What we lose is basically a factor that relates to how far we overshoot by shrinking, right? If beta you can see is very small, then this rate looks worse. But if we define some quantity t min to be the minimum between 1, this 1 is just referring to where we start each backtracking iteration. If we started at 100, then I would change that to 100. But in the slides, we always started at 1. The minimum between 1 and beta over L, then we get this bound. The suboptimality after k iterations is less than or equal to the square distance to the optimum divided by 2 times this t min times k. Okay? And we would still call this a rate 1 over k or 1 over epsilon, depending on how you parameterize it. OK. That's good news about backtracking. And let me tell you where you can, if you wanted to prove that for backtracking, take a look at this line. Remember, we achieved this line by starting with the Lipschitz condition and taking the step size small enough. What does this look like? It should look very familiar when you talk about backtracking. That's just the backtracking exit condition when alpha is a half. Right? This is guaranteed to be satisfied by backtracking when you take alpha to be a half. So at least the proof for alpha equals a half should be very straightforward. You basically start the proof right here. You can say this happens because of backtracking, and then you proceed as usual. OK, how about strong convexity? If we assume that the function itself is strongly convex, then we get a much better rate. So at a high level, remember, the Lipschitz being, the gradient being Lipschitz is like saying that the function can be upper bounded by a quadratic. Strong convexity is saying that the function can be lower bounded by a quadratic. That's something else that you're proving on the first homework. So that's actually telling us that our function has sufficient curvature, right? It can't be too flat. You can guess that with that additional assumption, you can prove a much faster convergence rate for gradient descent. And that is the case. This proof proceeds a little bit differently, but the high-level mechanics are similar. Just use strong convexity and definitions of convexity in order to get a bound on how far you are at a certain iteration. And then you add them up over all iterations to get an absolute idea of how far you are from the optimum. This proof, like I said, is in Boyd and Vandenberg's textbook. But the result is that with Lipschitz continuity of the gradient and strong convexity, after k iterations, the suboptimality looks like c to the k times the Lipschitz constant L over 2 times the square distance of where you started to the optimum. And this c is actually some number that's strictly less than 1. So under strong convexity, you get a much, much faster rate. We actually call this, in optimization terminology, we actually call this a linear convergence. So that might be confusing because c to the k it's actually exponential in k, right, if c is less than 1. So instead of ascending like 1 over k, it ascends like c to the k, where c is less than 1, which is a lot faster. Said differently, if I ask for this bound to be equal to epsilon, and I ask what does k have to be in order to get this bound equal to epsilon suboptimal, you can rearrange to see that means that k has to be on the order of log of 1 over epsilon. So I like this better because I think I like the epsilon notation better. I think it makes more intuitive sense. What happens if I told you that your function was, let's ignore all constants, your function was, had a Lipschitz gradient, and you want it to be like 10 to the minus 3 suboptimal. How many iterations would you need roughly with gradient descent? You need 10 to the 3, right? 1 over that iterations. How many iterations would you need with, let's say we're going to take that log to be base 10 even. How many iterations would you need with gradient descent if it was strongly convex? It's just log of 10 to the third, which is 3, right, if it's a base 10. So that's much, much faster. So there's a big difference between this kind of convergence rate and the one we derived earlier. The reason it's called linear convergence is because if you plot the criterion as a function of k, and you set the y-axis to be in a log scale, then it looks like a straight line. That's really the only, well, there's another reason I can give you for the terminology, but this one makes more sense to me at least. So people typically look at the convergence plots with a semi-log scale, so the y-axis is on a log scale, which means that you basically get a straight line descending on a log scale. And all the other convergence rates, like 1 over epsilon, is called sublinear, because that would lie somewhere up here. It would look like it's asymptoting almost. OK, what's important to point out is that despite the fact that we get this nice theoretical convergence rate, this constant c that we are taking c to the k, it depends adversely on the condition number, which means that if L over m is big, L is the Lipschitz constant of the gradient, m is the strong convexity parameter, then that c can be very close to 1. And in fact, you can get an explicit expression for c. You can check the Boyd and Vandenberg textbook for that, which means that you may not actually witness what we call linear convergence in practice if the problem is very poorly conditioned. It may actually look a lot worse than you might expect. Remember that also from your homework, L is an upper bound on the eigenvalues of the Hessian, and m is a lower bound. So this conditioning really refers to the Hessian matrix itself. If the Hessian matrix has a very big, largest eigenvalue and a very smallest eigenvalue, then the problem's poorly conditioned. And you may actually be seeing something more like the 1 over epsilon rate, even if theoretically it's converging at a rate log of 1 over epsilon. All right. I'm going to very quickly go through a look at the conditions. Then I guess I'm going to talk about, maybe I'll talk about forward stage-wise. We only have a few minutes left. So let's look at these conditions for a problem that we think about quite a bit, which is just regression, least squares regression. So suppose I'm trying to minimize the function y minus x beta and L2 norm squared. What does it mean for the gradient of f to be Lipschitz continuous in this case? It means, remember we saw on the homework, that means that the Hessian matrix of f has the biggest eigenvalue bounded by L. And if we take the Hessian of this criterion, then the Hessian is capital X transpose X. So that's our predictor matrix, the cross product of our predictor matrix. And its biggest eigenvalue is just the singular value of x squared. So I've denoted that by sigma squared of x, sigma max squared of x. So that's going to be true. And it's always going to be true. And that's going to be the Lipschitz constant for which it's true. So if we wanted to compute the Lipschitz constant, we have to actually find the biggest singular value of x. And once we've done that, we could then set the step size to be 1 over that if we wanted to. How about strong convexity? Strong convexity, you'll see, is much more dodgy of an assumption in this case because it's a lower bound on the eigenvalues of x transpose x. Now what happens if x has more columns than rows, which means that we have more features than observations? Then x transpose x is actually singular, right? So its lowest eigenvalue is 0, and it's not strongly convex. So in the high dimensional case, we don't have strong convexity. Even if it was strongly convex, which means that it has a lowest eigenvalue that's not 0, we see that actually the condition number is the ratio of its biggest to smallest singular values. Actually, it's the square of this ratio. There's a typo. So this can be very, very bad, right? If I have very correlated features in my regression, this can be very, very big. So I may not have a very fast convergence, even if I see it theoretically. Okay, so I think it helps to think about this problem to interpret the conditions. I didn't get to forward stage-wise. You guys are going to have a question on the quiz about these, so you're going to probably get mad at me. Let me just tell you that forward stage-wise is not gradient descent. It's very similar. It does something very similar. And so is gradient boosting. They're both variants on gradient descent. So you're going to be asked a quiz question about that. That'll be enough for you to answer it. Plus, the quizzes are worth tiny amounts. So let's just finish on the pros and cons, and then I'll let you guys go. So we're going to look at many other algorithms than gradient descent. This was like, you know, convex optimization like 101 was gradient descent for algorithms. What are its pros and cons? Pro, it's very simple, right? It's very simple to understand. It's usually very cheap to implement. All that requires is computation of the gradient. It usually doesn't cost much. And all you got to do is keep moving that direction. A pro is that it can be very fast for well-conditioned, strongly convex problems. So if your problem has a nice curvature, which means that it's strongly convex, and let's say it's well-conditioned, so the curvature actually is decent, then we get a log of 1 over epsilon convergence for gradient descent, which is very fast. That's how many iterations we need to get epsilon suboptimality. Con is that often, in practice, it's slow because the problems we want to solve are not well-conditioned, or they're not strongly convex. So we typically apply gradient descent to hard problems, and we don't really see that fast convergence rate. We just see the 1 over epsilon rate. And a bigger con is actually that we can't handle non-differentiable functions with gradient descent, right? We require, from the prescription we saw today, the criterion to be smooth. And that's going to be the bigger limiting factor, I think, for us when it comes to applying it. So we're going to see actually how to handle both of these issues over the next 3 lectures. We're going to see remedies for both of them. OK, that was it. See you guys on